Okay, good evening. Thank you for coming. This is the talk on resource management in Java. So I hope you all have the right room. This is the standard IBM disclaimer. And one day I'll get to read it all as well. Short introduction about me. My name's Neil Richards. I work in IBM. I have a couple of email addresses, one for IBM-related conversations, and one for correspondence under the terms of working in OpenJDK. I've been developing and deploying Java SDKs for about 15 years now, with no time off for good behavior. And previously, I've been the IBM technical component lead, amongst other things, for the I/O component networking and for the ORB supporting Corba and RMI over IOP. I currently work for IBM in OpenJDK on a number of different OpenJDK projects. And over the course of the work and my time, I've obviously seen a fair number of resource management related issues and worked on their solution. So what should we talk about this evening? Well, first of all, I'd like to define what resources I'm going to be talking about and what resources need managing. Then just lay out a couple of definitions and explore some approaches that there are in Java for dealing with native resource management, passive, active, and hybrid, and I'll define those things, how to use them, potential problems or traps to avoid when using them, and we'll look at some worked examples. Now, the worked examples, I've tried my best to get the code clear on the screen. It's really nice that I've got one nice large screen, and it's nice and high up, so hopefully everyone will be able to see clearly. If you can't, then just surreptitiously move forward, and that's great. We're all friends here. We'll also talk about limitations to each type of approach, and we'll end up with some recommendations that we draw out of wandering through these things together. So, what kind of resources need managing? It's good to compare and contrast the world of how things are in Java compared to how they were before Java, particularly in C and C++. To start with, you have artifacts which are allocated using stack memory as you make method calls, as you have local parameters which are allocated out of the stack, and you'll see that both in C and C++ and in Java, they're handled automatically. And I'll come back to the star in Java in just a moment. The major advance when we came to Java was that memory allocated from the heap is now automatically handled by the garbage collector in the JVM, and that helps to reduce a very frequent source of problems and errors when writing C code. But for other artifacts which are in the system, such as file descriptors, network sockets, database connections, and lots of other things, kind of anything you can really imagine, then there needs to be some extra intervention, both in the C++ world, but more interestingly for us, in the Java world. Now, the notes beneath here that in the Java case, or rather in the C case, you can, as well as kind of primitive variables allocated on the stack, you can also allocate structures on the stack. Whereas in Java, basically doesn't happen. If you want to have new objects, then they get allocated on the heap, and the only time when that doesn't happen is when the JIT in the VM is smart enough to work out that actually it can get away with allocating things on the stack instead. And the other note here is that although we say that heap memory is automatically allocated, automatically handled, freeing it up is automatically handled by the GC in Java, that still doesn't apply to memory that you've allocated for native methods and native resources, where you still have to worry about freeing them up yourself. So, some definitions. Basically, there are two. I'm using the term passive management to talk about those places where no requirements are laid upon the end user in order that the resources or the cleanup of the resources are handled. Whereas in opposition, active management are those techniques where there is some requirement on the end user to kind of comply in some way, use the code in some particular way in order that resources are properly handled. So on to our first approach, and we're going to look at the passive approaches first. So we'll look at finalization. Finalization, according to the Java language specification, provide a chance to free up resources that can't be freed automatically by an automatic storage manager, where automatic storage manager means GC. And it also says before the storage of an object is reclaimed by GC, the Java virtual machine will invoke the finalizer on that object. So this is good. This means that that you get a chance to do some cleanup of any native resources associated with the Java object, and you do that before the Java object itself gets cleaned up. How do you implement it? Well, you override the finalize method that is defined on Java lang object. That method is a protected method. So that any subclass, which means any type of Java class, can override it, and it throws throwable. So that seems kind of fairly simple. However, there are a number of different traps, a lot of which are also hinted at in the Java language specification. First of all, the Java programming language doesn't impose any ordering on the order in which finalize is called on objects. So finalizers can be called on objects in any order or even concurrently. So what does that mean? Well, it means that basically you can't, if a finalize method is called upon an object, you can't really rely upon the state of any any other object that object refers to. To be safe, you have to kind of limit yourself to just looking after cleaning up the resources which are really directly related to the object that you're dealing with. Secondly, it says that if an uncaught exception is thrown during finalization, the exception is ignored and finalization of that object terminates. That's kind of really scary. So that means that if you have any kind of exception or error that comes out from trying to free off the native resource, and you don't do anything special about capturing it and printing out that exception, then it will be silently eaten by the system, and you'll never get to find out about it until sometime later your application will fall over because it's run out of the native resources. Thirdly, unlike constructors, finalizers don't automatically invoke the finalizer for the superclass. Such an invocation must be coded explicitly. And I've rearranged the wording, the order of the words in the language specification, but I've preserved the meaning within there. And it says, this should always be done. It actually goes on to say, this should always be done unless there's some really amazingly good reason why you're absolutely confident that it shouldn't be. But that's really interesting. That has some so A, that's easy to omit. For a developer to omit, which is not good. Secondly, unless the class that you're implementing is declared as final, so that other people can subclass from it, then it means that your implementation of the finalize method needs to be protected. It can't be private or anything more restrictive, because you've got to allow the subclass to be able to call back to you. And it also has implications, as we'll see in the coding example, about the complexity of actually properly handling exception handling during the finalize method. And finally, it also says a finalizer may be invoked explicitly, just like any other method. So any place that has access through the protected accessor on the finalize method, which means anything in the same package as the class in question, as well as any subclass anywhere else, could call finalize prior to finalization. And so you need to have extra guarding code in there to handle that. And then there's some other traps as well, beyond those which you can pick out from the language specification or that lead on from it. So because finalize is protected, that means that when you use finalization and when you implement finalize on your class, it's part of that class's API. So even if at a later point you decide that actually you want to use an alternate technique and you don't want to use finalize anymore, you're kind of stuck with having the finalize method still there. So if you look at the code in the SDK for places that use finalize, you'll find an awful lot of the Java SDK code uses finalization as its mechanism for cleaning up native resources. And the reason for that is simple. Finalization was one of the first things that, the first ways of implementing these things that came along. And a lot of the Java classes associated with native resources, such as file descriptors and sockets and so forth, were also were there in early versions of Java. So they all implemented stuff on finalize. And now, even if they wanted to move off to use something else, they're still stuck with having finalize as part of their class's API. So more traps. It's fairly obvious, but only the implementer of the resource class itself can define a finalize method. So if you don't like the way that that a particular class has implemented finalize, then there's no way that you can replace it with your own or augment the behavior using finalization. One of the kind of most scary bits is in finalization, the developer still, because it's an instance method that's being called, you still have access to the reference to the object itself, and therefore you have all references to all other things that object refers to. And as I've already mentioned, those other objects may have already been finalized. They may be in the midst of being finalized, in the midst of actually running their finalize methods, or they may have yet to actually have their finalize method called, but be queued up, be scheduled to be finalized, in which case they will have their finalize method called, even though it hasn't already happened. And that's basically, that's all kind of quite dangerous because there's lots of temptation there to, and possibility to reach out and use bits of data and use the states of objects that are actually kind of stale and on their way to being finalized and being garbage collected, and kind of falsely use them as though they're live. And even worse, you might be tempted to grab hold of some of those objects or this object itself and try to resurrect them. Now, resurrecting them doesn't usually work as well as you would hope, because although finalize might be called on an object multiple times, it's only called once from finalization. So once an object has been called from has had their finalize method called from finalization, then if you resurrect it and move it back to be a live object, then the next time it loses its last strong reference, then finalize won't be called again by the finalization mechanism. It remembers that it has been called and it moves off silently, which is maybe not what you want. So here is our first example code. So just to go through this a bit. So it's my first resource thing. So it's my resource 1. We're going to have, so we're storing an opaque handle to our native resource in a long, which is what you normally do because you want to cater for being on, maybe on a 32-bit system, maybe on a 64-bit system. So a long is large enough to hold the native handle. We have a couple of native methods to allocate and free the native resource. And in here, we also are using an atomic Boolean to do the synchronization necessary to make sure that we're only going to try and call free native resource once. So in this case, in our construct is where we're going to call allocate native resource, and notice that we'll throw out any exception that we get as a result. If that goes awry. And then we've implemented our finalize method here, and this is the main line, which is saying, okay, we're going to try and change the value of closed from false to true in an atomic way using compare and set. And if that worked, then that means it was false before and now it's true, so we'll call free native resource. In all subsequent times when you're calling this, it will already be set to true, and so therefore this if block it won't go inside the if block, and so it won't call that. Now, so that's the simple thing of what's going on, and of course free native resource can itself throw an exception, but we also, due to what we saw before, we need to call finalize on our super class to be safe, and that also may throw a throwable. So we need to deal with the exception handling. We need to deal with that such that the call to super finalize doesn't prevent us from closing off our native resource, and closing off our native resource doesn't prevent calling super finalize, and an exception popping out from either one of those doesn't stop us from making the call to the other, and that we need to gather up the exceptions in such a way that we report it back consistently to up the stack. And because we know that actually when we throw the exception up the stack, it's just going to eat it and ignore it, we are going to capture it and print it out to standard error down here. So as you can see, the logic for doing that is pretty hairy, and Yeah, so that's incredibly easy to get wrong. So basically, you call each of these things. You save away on the first call. You save away the throwable that might be thrown, or the exception that might be thrown. You then always call the second call in the finally block of the first try block. You find out whether anything is thrown from that call, and then you kind of knit things up together using, in this case, I'm using the add suppressed feature, which actually came in Java 7 to help with that. So that's kind of what seems like it should be really simple is actually, even in the trivial case, really complex. Notice also, just a point, that in these examples, the classes which I'm showing, the operations on actually doing things with the handle once you got it, I'm leaving up to the reader. So we're only concentrating on the allocation and the deallocation of the resource and how that's handled. So that is finalization. We'll move on to the second approach, still passive approach, and this is using Java langref phantom references. So now this is from the Java 7 API Java doc, where it says phantom reference objects are enqueued after the collector determines, the collector being GC, determines that their reference may otherwise be reclaimed. And it says, it gives a suggestion that they're most often used for scheduling pre-mortem cleanup actions in a more flexible way than is possible with Java finalization. So I believe that phantom references came in about Java 1.4. So how do you use them? Well, as well as the resource class that we saw before, we're going to define a second class, a reference class, which subclasses phantom references, and we're going to use objects of that class type to track the main resource objects. We also need to create a statically held reference queue object, that is a Java langref reference queue object. And basically, the GC will place the instances of our reference class onto the reference queue at the point at which the resource objects are only referred to by the phantom reference objects or by the reference class objects. So the reference queue is effectively a source of the stale reference objects which need to be processed in some way. And the stale references can be removed from the queue in one of two ways, either by calling poll, which will return a reference from a stale reference from the reference queue if one is available, but won't block if one isn't available. And using that technique, using that approach, you usually cause poll to be called prior to each operation that you're doing using the handle. Or the other approach to doing this is to make use of the remove call on the reference queue. And the difference is the remove call will block. So in that case, you set up a dedicated background daemon type thread to sit on a call to the reference queue remove method, and then when it returns, it gives you back a reference object that has been queued up, a stale reference object that's been queued up for processing. So there are some traps associated with using phantom references too. Again, from the Java doc, it says if the garbage collector determines at a certain point in time that the referent of a phantom reference is phantom reachable, then at that time, or at some later time, that's my emphasis, it will enqueue the reference. So that suggests with a certain amount of surety that there is some delay in actually seeing references being placed on the reference queue. So it's at some point after GC has identified that the resource object is otherwise eligible for garbage collection that it queues it up. The second thing is it says the get method of a phantom reference always returns null. Now, most references, or all the other types of references that there are, they have this get method, and the object that is associated with the reference object when the reference object is created, is instantiated, the get method is designed to, would normally return a reference to that object. But it's very purposeful that the phantom references always return null from the get method. The whole point is this is there in order to prevent you from accessing otherwise stale resources which are in the object. So when I was talking about finalization, I said it's dangerous that you get a reference back to this. So this is the thing that effectively prevents you from getting the equivalent because you can't get a reference back to the real reference object. The implication of that is that anything that you actually need to do, that you want to do as part of processing this stale reference, is any information that you need to store upon the reference object itself and not upon the resource object. So we'll see that when we get to the code example. And thirdly, an object that's reachable by phantom references will remain so until all such references are cleared or themselves become unreachable. So this is really interesting and a little bit odd, because although you can't, there's no way of getting a reference to the object that the reference object is tracking back from the phantom reference. Nevertheless, that object is still remains phantom reachable until such point as you've dealt with and thrown away all the phantom references. And whilst that object is phantom reachable, the garbage collector won't actually free up the memory associated with that object, even though you can't get at it anymore. And I can only assume that there's some deep fundamental reason, from a VM's point of view, why that's a really good idea. Furthermore, you must make sure that when you're using phantom references, that a strong reference needs to be maintained to the phantom reference object itself. If you don't do this, then if the phantom reference becomes eligible for garbage collection, then it will be garbage collected and it won't get posted onto the reference queue. So just because you created a phantom reference object saying I want it to be posted onto a queue, onto this reference queue when the associated object that it's referring to becomes eligible for garbage collection. Nevertheless, if the phantom reference object itself gets garbage collected, then you don't get any notification at all. So you have to keep a reference to that strongly, and obviously once you've seen it come out of the reference queue and it's stale, and you've done the processing to do whatever cleanup it is, then you need to free off this strong reference, because otherwise you'll have a memory leak of ever-increasing number of phantom reference objects around. However, there are benefits of using phantom references over finalization. I've mentioned it, I've already talked about this, but the benefit, as well as the pain, is that you can't get back a reference to the resource object from the reference object using the get method, and that makes the code safer and therefore easier to understand. There's no interference between finalization and phantom reference uses in superclasses. So because an object could be tracked in a number of different places by a number of phantom reference objects, all with their own particular purposes. And so therefore the kind of interaction, remembering that you have to call a method on your superclass and dealing with any exceptions which might happen in the finalization, in the cleanup associated with your superclass is something that doesn't interfere with your coding using the phantom reference. So it avoids all that complicated coding for exception handling, and because you can also the implementation of the phantom reference can be external to the resource class that you are dealing with. This means that you can also use it to track. You can track resources that you haven't actually had a hand in writing. You don't need to be modifying those classes at all, but you can use phantom references to track them and to deal with them. So I'll examine that a little bit more later. Here's the example code for phantom references. So you'll notice that now the handle is now within the reference object, which is extending phantom reference. We have within here, we have a static set of active references. So when we allocate things, we synchronize on that set and we add the new reference object into that set. That's what maintains the strong reference so that it is going to get queued out at the end. Then deactivate is a method which will return Boolean the first time that it's will effectively look and try and remove the reference from the set of active references, and the first time that this is called, it will succeed, and subsequent times it will fail, and when it succeeds it returns true, so that then in close, instead of using the atomic Boolean, we call deactivate, and if deactivate returns true, then we call free native resource. So this is also using our first approach, which is going to be using poll to look at the reference queue, which is also held statically up here, as I said. So we have a process queue method here and some more stuff which we'll look at in the next slide. So process queue expanded is just going to sit in a do while loop whilst we actually get something back from call to poll on the reference queue. If we get back a null, then we break out of the do while loop and return. And we're still capturing the exception and printing out the stack trace of it if things go wrong. And basically, for each operation to do with the resource, then you have to remember that there's to make a call to the process queue method, so that you're going to clear out and process any stale references. So that is that. Also notice here that I'm only synchronizing on the stale references here during the poll call. So I'm allowing the possibility that this call to close may take a long time, as it may well do, and so I'm not holding on to the monitor for the stale references queue whilst I'm making the call to close. So the alternative is to use a thread so here we have a Reaper thread that when we create it, we say it's a daemon thread, and we start it up, and then instead of calling poll, we're calling remove, and the run block is just a do while loop, which just keeps on going until the end of the Java process itself. And then that eliminates the need for having a process queue method, and also eliminates that call that needs to be made on each operation. So those are the two passive approaches. The general limitations here, they can only be, resources can only be found as stale once GC has happened, and GC might be conservative, so there's actually no guarantee that stale resources are found even after GC has happened. GC is generally triggered by a constraint of Java heap memory, which is a different type of resource. So perversely, if you have a larger Java heap, then it can be longer before it's spotted that other resources or objects associated with other native resources are ready to be closed. And so you can run a greater risk of getting an out-of-memory error due to the exhaustion of other native resources. And that's a really weird thing when you see it. It's completely counterintuitive to think that by reducing the size of the Java heap, you might actually lessen the chance of getting out of memory. So GC, so the other thing is that GC, through finalization or phantom references, the objects themselves are delayed GC from actually being able to free up the memory associated with those resource objects. So finalizable objects are processed on the finalization threads, so they have to actually get through that and have the finalize method called, and then another GC cycle happen in order to spot and to free up the memory, and references need to be removed from the reference queue and whatever processing done for them before their memory gets freed up. So the result is that you actually get more constraint on the Java heap and more time is spent performing GC. So on to active approaches. Now, the first approach here I describe as management by fiat, which is not what you think, but I'm using the definition of fiat, arbitrary order or decree. So this is basically, we've already actually done this in our previous example, but providing a method or resource on an object to release the underlying resource, and then generally called something like close, and then telling the users of the class that they need to call that method in order to free the resource. This is effectively exactly what happens when you're dealing with resources in C. It's helpful if the function that you're defining is idempotent. And I'm going to skip through that, but idempotency basically means that it behaves precisely the same way the subsequent times to how it behaves the first time that you call it. So it doesn't complain that if you call close the second time, it doesn't complain that the resource is already closed off. It just says, yeah, just returns normally and says, yes, it's been cleared off. So the obvious traps are, it relies upon the user actually calling the close method. It's sometimes tricky for the user to know exactly when the correct time to call close is, but use of try finally blocks will help there. And again, if you're closing off a number of resources, you get to the same type of complexity in exception handling that we saw in our first case. So that the exceptions are all handled properly. Here, but so here we are. We're back to using atomic Boolean here. We're specifying this close method, and it's all, it's pretty straightforward in this simple case. But as I say, the exception handling, if you're dealing with it in more than once. So up here, basically the pattern is that you create your new resource object. You then immediately after start a try block do whatever it is that you want to do with a resource within that try block, and then in the final block you call close to make sure that close is called correctly. The second approach is using a thing called automatic resource management, or try with resources. This came in Java 7, and it's possibly the best language feature ever in my humble estimation. You implement it by having your resource implement auto-closable, which has one method which needs to be implemented, which coincidentally is also called close and throws exception, as we had before. And basically, auto-closable objects which are assigned within, parentheses were introduced in Java 7 for try blocks, and auto-closable objects which are assigned to variables within those parentheses are automatically closed at the end of that try block. So it implicitly generates all the nasty, complex, finally logic and exception handling code for you, so you don't have to, which is why it's the best feature ever. It allows you to do support multiple assignments in the same try block, and it's really fab. There are a few traps with it. First of all, the user still needs to comply with using it with the try with the resources type syntax, though they might choose to call close directly because, hey, it's just a method, and if they call close directly, then they lose all the magic exception handling code that gets generated or that gets created if you use the try with resources approach. Also, the other slight catch is just to emphasize that it's the auto-closable objects which are assigned to variables in the parentheses of the try block that are handled, and not those that are allocated. So, for instance, if you are creating a print writer which a new stream writer to put into a new print writer, and it's best to have them both be closed at the same time. You actually need to have two statements. You need to have a statement which creates the string writer, assign it to a variable, and then a second statement still within the parentheses of the try block, which creates the print writer object and assigns it to a second variable, and then everything will work happily. And the final thing is you need to be running on Java 7, which we all want to, and sometimes, you know, corporate edict or whatever means that that can be more problematic. So here we are. We have this is a try with resources. We've got two resources here. We do stuff with myres1 and myres2 inside this block, and then when we come out of the try block, all the finalization, all the exception handling gets handled for us. We then this comment has expanded to say, hey, we can use try with resource. We've got implemented auto-closable. This is our public close method. Other than that, it's all the same. So, general limitations to the active approaches. Because the objects are still strongly referenced at the point at which their methods are called, so user code may be able to see resource objects that have actually been closed out. So you need to have some guard checking in the operations on your resources to check whether it's still active, whether it's still live or not, whether it's been closed off or not. And there's no guarantees that the user will actually follow instructions to call the methods or use try with resources, and that's a point that's, you know, worth emphasizing again. So there are these problems with both approaches, but by using a hybrid approach, you can get the best of both worlds. You use the active approach to allow the user to be able to free off the resources in a timely fashion, and you use a passive approach to verify that the user has freed off the resources, and if they haven't freed off the resources, to print out an error saying that's happened. So there's an example with the combined approach that we have here. In this case, so we're using autoclosable, and we're also using phantom references. So the autoclosable is the active approach, and the phantom reference is tracking that things have happened correctly. And what we're doing is, when we create the phantom reference, we're going to create an exception object which contains the call stack of the at the point of construction. And then later on in the Reaper thread, if we find out when we remove the stale reference that the stale reference we've removed is still in the set of active references. So back here, so here this is a close method. So this will free off the native resource the first time that we call deactivate. So here, if we call deactivate and it's telling us this is the first time it's been called, then that means that the user hasn't done their job and hasn't called close either with the try resources or directly. And so at that point, we can now print out an error message saying that the user hasn't done their job, and we can use the call stack that we captured in the exception at creation time to give a good clue to the user about where it is that they're going wrong. Because at the point at which you detect this, you're in some completely different, well, you're on a completely different thread because you're on the Reaper thread when you're seeing that. So the recommendations are to use the active approach to allow the user to swiftly free resources, implement autoclosable so that they can use all the try with resources magic, use a passive approach to monitor to make sure that the user has freed things off. And you can use that approach even to monitor that kind of standard Java resources that are particularly key to your application have been handled correctly by the user. It's preferable to use phantom references over finalization because of the ease of doing correct implementation and the flexibility to possibly track standard resources, and to fail fast if you detect that that resource is leaking. It's best to tell the developer early on at the first instance where you detect it that they're not doing something right, rather than trying to kind of soldier on manfully. And to use both approaches in combination so that the user can free things off in a timely manner, and so that you can monitor and report for resource leakages due to that not happening. And there's another bit of IBM boilerplate just to finish off the presentation. Thank you very much.